Let us begin with the first and most humbling obstacle to alien visitation: the sheer scale of the cosmos. When we say space is big, we commit an understatement so severe that it borders on deception. The universe is not big in the way oceans are big, or continents are big, or even planets are big. It is big in a way that strains language, fractures intuition, and dismantles imagination. To understand why it may be physically impossible for aliens to ever reach Earth, we must first confront this scale honestly, not poetically, not optimistically, but numerically. This is exactly the kind of problem Richard Feynman would insist we examine. Feynman had a habit of cutting through fantasy with arithmetic. He believed that nature cannot be fooled. You can hope, speculate, dream, but when you put numbers on paper, the universe answers with ruthless clarity. Let us start close to home. The Earth orbits the Sun at an average distance of about 150 million kilometers. That distance is so large that light traveling at 300 kilometers per second still takes about 8 minutes to reach us from the Sun. 8 minutes moving at the fastest speed allowed by physics, just to cross our own solar neighborhood. Now extend outward. The outer boundary of our solar system, depending on definition, stretches trillions of kilometers. The Voyager probes, launched in the 1970s, have been traveling for nearly half a century and have only just entered interstellar space. They are moving at roughly 17 kilometers per second. At that speed, reaching the nearest star would take over 70 years. And the nearest star system is not across the galaxy. It is right next door in cosmic terms. That system is Alpha Centauri, located about 437 light years away. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. Multiply that by 437. The number becomes almost abstract, over 40 trillion kilometers. To visualize this, imagine shrinking our solar system so that the Earth's orbit fits inside a coin. On that scale, the nearest star would be thousands of kilometers away, not across a room, not across a country, across continents, and this is just the nearest star. Our galaxy, the Milky Way, contains roughly 100 to 400 billion stars. It spans about 100 light years from edge to edge. If an alien civilization existed on the opposite side of our galaxy and somehow managed to travel at light speed, which physics forbids for anything with mass, the journey would still take 100 years. That is longer than human civilization has existed. Human recorded history stretches back perhaps 50 years. Agriculture began roughly 10 years ago. Homo sapiens as a species are around 300 years old. Crossing the Milky Way at light speed would take a third of our species' entire existence. And remember, light speed is unattainable for spacecraft. Even if a civilization could travel at 10% of the speed of light, an achievement far beyond anything humanity can currently imagine, crossing the galaxy would take 1,000,000 years. 1,000,000 years, civilizations rise and fall in centuries, languages evolve in thousands of years, stars themselves move in their orbits during such timescales. To plan a journey lasting 1,000,000 years requires not only technology, but cultural continuity beyond anything we observe in nature. Feynman would ask a simple question: where is the mechanism that makes this practical? Because distance is not just a number. Distance multiplied by finite speed becomes time, and time is the true barrier. We often imagine alien spacecraft zipping effortlessly between stars, as if the galaxy were a neighborhood. But this intuition comes from living on a planet where global travel takes hours. The step from airplane to starship feels like an engineering upgrade. But it is not. It is a leap across scales so enormous that comparison becomes meaningless. Let us continue expanding outward. Beyond our galaxy lie other galaxies. The nearest large galaxy to us is Andromeda Galaxy, approximately 2.5 million light-years away. If an alien civilization lived there and launched a spacecraft toward Earth at light speed, it would arrive 2.5 million years later. 2.5 million years ago, early human ancestors were just beginning to use primitive stone tools. Think about that. If someone in Andromeda aimed for Earth during that era, their ship would be arriving today to a completely transformed planet, with an intelligent species that did not even exist when they launched. Now consider the observable universe, which spans about 93 billion light-years in diameter. There are estimated to be hundreds of billions, perhaps trillions, of galaxies. The sheer distribution of matter is so sparse that even within galaxies, stars are separated by unimaginable gulfs of emptiness. Space is not filled with convenient stepping stones. It is mostly vacuum. The average density of matter in interstellar space is about 1 atom per cubic centimeter. It is a desert more barren than anything on Earth. When science fiction depicts alien invasions, it compresses this scale into something psychologically manageable. Ships hover over cities. Armadas gather near planets. But physics does not compress distance. It enforces it. Even traveling to Mars, our planetary neighbor, requires months with current technology. Mars is, on average, about 225 million kilometers away. That is nothing compared to the trillions of kilometers between stars. The jump from interplanetary to interstellar travel is not incremental. It is exponential. Imagine swimming across a pool, difficult but feasible. Now imagine swimming across the Pacific Ocean. The difference is not merely distance. It is survival time, resources, environmental hazards, and biological limits. Interstellar space is the Pacific Ocean of the cosmos, but colder, emptier, and far more unforgiving. The cosmic scale problem becomes even more severe when we consider motion. Stars are not stationary. The Sun orbits the center of the Milky Way at about 220 kilometers per second. Other stars move at their own velocities. Over tens of thousands of years, relative positions change significantly. Planning an interstellar journey requires calculating not where a star is now, but where it will be centuries or millennia in the future. Miss by a fraction of a degree, and you drift into empty space forever. Feynman would emphasize that nature does not care about intention. If your trajectory is off by the smallest margin across light-years, you do not arrive slightly late. You miss entirely, and then there is expansion. On cosmic scales, the universe itself is expanding. Distant galaxies are receding from us, carried by the expansion of space. Beyond a certain distance, galaxies recede faster than light due to the expansion metric. That means some regions of the universe are permanently unreachable, even in principle. The universe has horizons. There are places from which light emitted today will never reach us, no matter how long we wait. And there are places we can never reach, no matter how advanced we become. Distance, in cosmology, is not merely separation. It is sometimes permanent isolation. All of this leads to a sobering conclusion. The universe is structured in such a way that interaction between civilizations is not simply difficult. It may be statistically negligible. Even if intelligent life is common, The spacing between technological civilizations could be thousands of light years. At sublight speeds, that means travel times of tens of thousands of years. Communication alone would require millennia for a round trip. Imagine sending a message and receiving a reply 20,000 years later. Civilizations may not survive long enough for dialogue. Feynman once said that the universe is under no obligation to make sense to us. The cosmic scale problem is a perfect example. Evolution on Earth prepared us to navigate forests and plains, not to intuitively grasp distances measured in trillions of kilometers. Our brains evolved for survival at human scale. Interstellar scale defeats intuition. Let us perform a mental compression exercise. If the Sun were the size of a grain of sand, Earth would be a microscopic speck orbiting a few centimeters away. On that same scale, the nearest star would be several kilometers distant, and the Milky Way would span the width of a continent. Now ask yourself, how likely is it that civilizations separated by continental distances of sand grains will casually visit one another? The answer is not emotional, it is numerical. Even optimistic theoretical propulsion concepts, nuclear fusion drives, antimatter engines, laser sails, face the same core constraint. Distance divided by finite speed equals enormous time. And time multiplies every other challenge. Life support must function for centuries. Machines must endure micrometeoroid impacts for millennia. Social systems must remain stable for generations born and dying aboard a vessel that may never see its destination. Distance turns engineering into civilizations. Gale endurance. The first keynote, the cosmic scale problem, is not dramatic. It does not rely on exotic physics or speculative impossibilities. It relies on multiplication. Light travels fast. Space is enormous. Multiply the two. The result is time measured not in years, but in epochs. And this is only within our galaxy. When we step back and look at the universe as a whole, we realize something profound. The cosmos is not arranged like a tightly connected web. It is more like scattered islands across an infinite ocean. On Earth, islands can be bridged by ships in days. In space, the ocean between stars requires decades, centuries, or millennia, even at unimaginable speeds. If alien civilizations exist, they may be thriving in their own stellar neighborhoods. They may have art, science, and philosophy. They may look at their sky and wonder if someone else is out there. But the gulf between wondering and arriving is written in light, years. Feynman would not say aliens are impossible. He would say that visiting us requires overcoming numbers that are brutally indifferent. The cosmic scale problem alone forces us to confront a hard truth. The universe may be full of life, yet effectively silent. Not because no one exists, but because the distances are so vast that reaching across them may be physically impractical beyond any reasonable expectation. And this is only the first barrier. The universe begins by separating us with space, not metaphorical space, but measurable, calculable, relentless space. When we truly absorb that scale, the idea of alien spacecraft hovering over Earth stops being a technological question and becomes a physical one. The cosmos is not a neighborhood. It is an abyss measured in light, years. When we continue examining the cosmic scale problem, something even more unsettling emerges. It is not only that space is vast, it is that emptiness dominates that vastness. The universe is structured less like a crowded city and more like a nearly infinite desert with rare, isolated oases. And when distances between oases are measured in light, years, even the possibility of travel becomes a question not of ambition, but of survivability across time. Richard Feynman would remind us that the universe operates on principles that are not negotiable. You can invent technologies in imagination, but you cannot invent away distance. The numbers remain, and when you begin calculating travel across even modest portions of our galactic neighborhood, the scale problem intensifies in ways most people never fully consider. Let us think statistically. Astronomers estimate that the Milky Way contains hundreds of billions of stars. That sounds crowded, but galaxies are enormous volumes. The average distance between neighboring stars in our region of the galaxy is roughly 5 light-years. 5 light-years of mostly nothing. Imagine standing on a planet orbiting a star 5 light-years away from Earth. Your civilization develops radio. You detect faint signals from a small blue planet around an ordinary yellow star. You identify artificial transmissions. You confirm intelligent life. Now what? At the speed of light, your signal announcing discovery will take 5 years to reach Earth. If Earth replies immediately, that reply takes another 5 years. A single exchange requires a decade. That is just communication. If you attempt travel at, say, 10% of light speed, an extraordinary engineering achievement, the journey would take about 50 years. That is one way. If you travel at 1% of light speed, it takes 500 years. And these numbers apply to our nearest stellar neighbors. Most stars in the galaxy are hundreds or thousands of light-years apart from us. The moment you move from tens of light-years to thousands of light-years, the timescales explode. At 1% of light speed, a 1,0,00 light-year journey requires 100 zeros, 00 years. That is longer than recorded human history by a factor of 20. Distance multiplies into time. Time multiplies into generational turnover. And generational turnover multiplies into uncertainty. A civilization planning such a mission would have to assume that the target planet will remain habitable and technologically relevant for tens of thousands of years. But planets change, civilizations collapse, species go extinct. When humans built the pyramids, we had no electricity, no steel skyscrapers, no digital networks. Imagine launching a mission then, expecting to arrive in 2026. The destination would be unrecognizable. Now scale that to 50 zeros, 00 or 100 zeros, 00 years. By the time an alien spacecraft arrives, Earth could be ice, covered ocean, covered, technologically advanced beyond recognition, or entirely devoid of intelligent life. The target is not static, it is evolving. Feynman would insist that we treat moving targets seriously. In physics, if you fire a projectile at something moving unpredictably, the odds of success diminish rapidly with distance and delay. And the galaxy itself is dynamic. Stars orbit the galactic center. They oscillate above and below the galactic plane. Over tens of thousands of years, relative stellar positions shift significantly. Navigating across light-years requires extreme precision in predicting gravitational influences over millennia. A tiny miscalculation at departure becomes a catastrophic miss at arrival. Then consider stellar hazards. The galaxy is not empty in a perfectly clean way. It contains interstellar gas, dust clouds, magnetic fields, and high-energy cosmic rays. Over long durations, exposure to radiation accumulates damage. Even at low densities, interstellar dust particles striking a ship traveling at significant fractions of light speed would impact with tremendous energy. A grain of dust at relativistic velocity carries the kinetic force of an explosive projectile. Over decades of travel, countless such impacts would occur. Shielding must be massive. Mass increases fuel requirements. Fuel increases mass further. The exponential burden grows. Distance does not just require endurance, it compounds engineering constraints. Now expand perspective further. The observable universe contains not just one galaxy, but hundreds of billions, perhaps trillions. The nearest large galaxy beyond our own, the Andromeda Galaxy, is approximately 2.5 million light-years away. At 10% light speed, the journey would take 25 million years. At 1% light speed, 250 million years. On Earth, 250 million years ago was the time of early dinosaurs. To embark on a journey of that duration would require a civilization to commit to a timeline longer than the lifespan of most species. Evolution itself reshapes life over such intervals. The beings who depart would not be the same as the beings who arrive, if arrival even occurs. And this reveals a subtle but crucial aspect of the cosmic scale problem: the mismatch between biological timescales and cosmic distances. Life evolves over millions of years. Civilizations rise and fall in thousands. Political systems change in centuries. Technological paradigms shift in decades. But crossing the galaxy at sub-light speeds demands tens of thousands to millions of years. The scales are misaligned. Even if a species achieves extraordinary longevity, extending life spans to thousands of years, it still faces travel times exceeding individual existence. Multi-generational shifts introduce sociological complexity. Entire societies would live and die en route. Cultural drift becomes inevitable. The mission's original purpose may be forgotten, reinterpreted, or rejected. Distance magnifies entropy, not just physical entropy, but social entropy. And then there is probability. Suppose intelligent civilizations are rare. Suppose there are only a few thousand in the entire galaxy at any given time. Spread across 100,000 light years, the average separation could be thousands of light years. Communication delays stretch into millennia. Travel becomes a commitment across epochs. Even if civilizations are common, say millions exist, the density is still low compared to the volume of the galaxy. Space between stars is vast. Space between technological species may be vaster still. The cosmic scale problem thus intersects with statistics. Low density across enormous volume yields extreme separation. Feynman often emphasized that nature's numbers are not sentimental. They do not shrink because we prefer companionship. Now consider cosmic expansion. On the largest scales, space itself expands. Distant galaxies recede from us due to the expansion of the universe. Beyond a certain distance, the cosmic event horizon, objects move away effectively faster than light, because space itself stretches. Signals emitted today from beyond that horizon will never reach us. Similarly, we can never reach them. There are regions of the universe permanently disconnected from us, not because of technology limits, but because of geometry. The structure of spacetime imposes isolation. This means that even if advanced civilizations exist in distant galaxies, they may be fundamentally unreachable, not just practically, but in principle. The universe contains built-in boundaries. Now step back emotionally. Human beings evolved under a sky where stars appear close together. To the naked eye, the night sky feels intimate. Constellations give the illusion of structure and proximity. But those stars are separated by light years. The patterns are projections on a dome, not clusters in a neighborhood. Our perception deceives us. The cosmic scale problem is, at its heart, a failure of intuition. We evolved to judge distances in meters and kilometers. Even planetary distances strain comprehension. Interstellar distances shatter it. If the Earth were reduced to the size of a marble, the Sun would be several meters away. On that same scale, the nearest star would be thousands of kilometers distant. The Milky Way would span continents. And between those scaled stars, nothing. Imagine marbles scattered across Earth's surface, separated by thousands of kilometers. Now imagine intelligent microbes living on one marble, trying to visit another using chemical propulsion. The analogy still understates the challenge. Distance is not just a measurement, it is a filter. It filters out easy contact. It filters out casual exploration. It filters out impulsive travel. To cross interstellar space requires civilization, level planning, energy reserves rivaling planetary output, engineering resilience beyond current imagination, and patience measured in centuries or millennia, and all of this assumes motivation strong enough to justify the cost. Why would a civilization commit vast resources for generations to visit a distant biosphere when local exploration may already provide endless opportunity? The galaxy contains billions of stars. If life emerges occasionally, there may be closer targets than Earth. The cosmic scale problem does not merely challenge feasibility, it reduces likelihood. In physics, impossibility can mean two things: absolute prohibition by law, or practical impossibility due to overwhelming constraints. The first keynote leans heavily toward the second category. The laws of physics do not forbid interstellar travel outright, but the combination of immense distances, finite speed limits, energy demands, and temporal scales pushes feasibility toward vanishing probability. And probability matters. If something is technically possible, but requires such extreme coordination and endurance that almost no civilization could sustain it, then, for all practical purposes, contact becomes unlikely. Feynman valued intellectual honesty. He would caution against declaring absolute impossibility prematurely. But he would also insist on respecting scale. When you multiply trillions of kilometers by strict speed limits, when you extend travel times into tens of thousands of years, when you layer in stellar motion, radiation hazards, sociological instability, and cosmic expansion, the picture becomes clear. The universe is not arranged for easy visitation. It is arranged for separation, and this separation is not malicious. It is structural. Stars formed from collapsing clouds of gas billions of years ago. They ignited nuclear fusion. Planets coalesced from debris. Life emerged under local conditions. Each stellar system became its own island of chemistry and evolution. The distances between those islands are so vast that even light, the fastest messenger in existence, requires years to cross the gaps. When we fully absorb this, we begin to see why alien arrival narratives clash with physical reality. The first barrier is not hostility, it is scale. Before we ever discuss speed limits, energy catastrophes, radiation hazards, or relativistic time dilation, we must confront the fundamental architecture of the cosmos. It is enormous beyond comfort, it stretches beyond instinct, and it separates civilizations, if they exist, by gulfs that demand not just technology, but endurance across ages. That is the cosmic scale problem, and it stands as the first, silent, immovable wall between Earth and any distant intelligence that might wonder about us from beneath another star. When we move from the sheer size of the cosmos to the second barrier, the challenge becomes even more unforgiving. Distance alone is terrifying, but distance combined with a universal speed limit becomes something far more severe. The second keynote confronts a principle that is not technological, not economic, not cultural, but fundamental to the structure of reality itself. Nothing with mass can reach or exceed the speed of light. This is not a limitation imposed by current engineering. It is not a matter of insufficient fuel or primitive materials. It is a structural rule embedded into spacetime. And to understand why this rule changes everything about alien travel, we must think with the clarity and discipline of Richard Feynman. Feynman insisted that physical law is not negotiable. Nature does not compromise. If an equation says something requires infinite energy, then infinite energy is not a challenge to be solved, it is a prohibition. The speed of light in vacuum, approximately 299,792 kilometers per second, is not simply the speed at which light happens to travel. It is a conversion factor woven into the structure of spacetime. It defines how space and time relate to one another. And according to the theory of relativity developed by Albert Einstein, this speed represents an absolute upper limit for anything carrying mass or information. To appreciate the severity of this limit, we must move beyond slogans and examine consequences. Imagine accelerating a spacecraft. In classical physics, if you push something harder, it moves faster. In principle, there is no upper limit. But relativity changes that intuition. As an object accelerates toward light speed, its relativistic mass increases. More precisely, its energy increases dramatically according to the Lorentz factor. The closer you get to light speed, the more energy you must invest for each additional increment of velocity. At low speeds, the energy increase is manageable. At high speeds, it becomes staggering. As velocity approaches light speed, the required energy approaches infinity. Not very large, not astronomically high, infinite. Infinite energy is not a matter of advanced engineering. It is a mathematical divergence. The equations simply do not permit further acceleration. This means that no matter how advanced an alien civilization becomes, if they obey the same physical laws we observe, and all evidence suggests physical laws are universal, they cannot accelerate. A spacecraft with mass to light speed, let us consider what this implies for interstellar travel. Return to the nearest star system, Alpha Centauri, about 4.37 light years away. If you could travel at exactly the speed of light, you would arrive in 4.37 years from Earth's perspective. But you cannot, so let us consider 90% of light speed. That is unimaginably fast compared to current human capabilities. At 90% of light speed, the Lorentz factor is about 2.29. That means the kinetic energy required is more than double what Newtonian intuition would suggest. As you push closer 99% of light speed, the Lorentz factor rises to about 7.09. At 99.9%, it jumps to about 22. And at 99.999%, it explodes into the hundreds. Each additional decimal place demands disproportionately greater energy. The curve steepens violently. To accelerate even a modest spacecraft weighing, say, 0.0 tons to 99% of light speed would require energy comparable to the total energy consumption of humanity over many years. And that accounts only for acceleration. You must also decelerate upon arrival, doubling the requirement. If a civilization attempted to send thousands of such vessels across the galaxy, the energy demand would rival stellar output. Feynman would ask, where does that energy come from? Not in imagination, but in physical accounting. Even if an advanced civilization harnessed the total output of its star, constructing megastructures to capture stellar energy, converting that energy into propulsion with near-perfect efficiency, presents another challenge. Real systems are never perfectly efficient. Entropy extracts a cost. Waste heat must be radiated away. Engineering constraints multiply. The speed limit is not simply about velocity. It is about energy scaling. Let us explore a hypothetical. Suppose an alien civilization develops propulsion capable of reaching 50% of light speed. At that velocity, travel to Alpha Centauri would take roughly 9 years from Earth's frame. That seems manageable. But consider a target 1,000 light years away. At 50% light speed, that journey requires 2 zeros, 0 years from Earth's perspective. Civilizations do not remain static for 2 zeros, 0 years. Even human civilization has transformed beyond recognition in just the past 200 years. Now suppose they aim for a star 10,000 light years away, still within our own galaxy, the Milky Way. At 50% light speed, that is a 20,000 year journey. Even at 90% light speed, 10,000 light years still requires over 11,000 years of travel time in the stationary frame. The speed limit enforces these timescales relentlessly. One might argue that time dilation benefits the traveler. Indeed, according to relativity, time slows down for objects moving at high velocity. From the perspective of those aboard the spacecraft, the journey could feel shorter. But this does not eliminate the problem. It merely shifts frames. From Earth's perspective, or from the galaxy's broader timeline, thousands of years still pass. Targets evolve, stars move, civilizations rise and fall. A ship may experience 50 years subjectively, while 5 zeros, 0 years pass externally. Relativity does not remove the cost, it redistributes it. Now consider communication. Even if aliens do not physically travel, signals are bound by the same speed limit. Radio waves move at light speed. If a civilization 5,000 light years away detects our broadcasts, their reply will take 5,000 years to reach us. A simple exchange becomes a 10,000 year dialogue. In that time, languages change, species evolve, planets shift. The speed limit converts cosmic curiosity into generational silence. Feynman emphasized that when you truly understand a law, you accept its consequences without complaint. The speed of light limit is not an inconvenience. It is foundational. Without it, causality could break down. Effects could precede causes. The structure of spacetime would unravel. The same constant that prevents alien starships from casually visiting also preserves logical order in the universe. There are speculative ideas, warp drives, wormholes, spacetime shortcuts, theoretical constructs inspired by solutions to Einstein's field equations. But every such concept faces severe obstacles: exotic matter requirements, negative energy densities, quantum instability. To date, no experiment has demonstrated faster than light travel or communication, and Feynman would insist on experimental evidence over mathematical fantasy. Even if wormholes exist naturally, they would require stabilization beyond known physical mechanisms. And if warp metrics are mathematically allowed, the energy requirements may exceed the mass energy of entire stars. When physics suggests something requires negative energy comparable to planetary mass, skepticism is not pessimism. It is discipline. Now widen perspective again. The observable universe spans roughly 93 billion light-years in diameter. Even at light speed, reaching distant galaxies would require tens of billions of years, longer than the current age of the universe, about 13.8 billion years. And because of cosmic expansion, some galaxies recede so rapidly that light emitted now will never reach us. They move beyond our cosmological event horizon. The speed limit intersects with expansion to create permanent isolation zones. Even if aliens in a distant galaxy desired to reach Earth, they may be carried away faster than any signal or spacecraft could traverse the expanding metric of space. This is not technological failure. It is cosmological structure. The universe enforces separation through geometry and velocity limits simultaneously. And so we confront the stark implication of the second keynote. Intelligence does not override relativity. No matter how advanced a civilization becomes, it cannot outrun spacetime itself. The cosmic speed limit transforms interstellar travel from a matter of courage to a matter of exponential energy scaling and epochs, banning endurance. Even optimistic projections, 10% of light speed, 20%, 50%, leave journeys measured in centuries or millennia for significant fractions of the galaxy. If civilizations are separated by tens of thousands of light-years, then even near light-speed travel demands time commitments rivaling evolutionary epochs. The speed limit ensures that the universe is not a tightly connected network. It is a realm of causally separated regions, linked only by light cones that expand at a finite rate. Feynman often delighted in the elegance of physical law. The same equations that describe particle accelerators describe galaxies. The same limit that governs electrons governs starships. There is a quiet symmetry in that. We may imagine alien technology surpassing ours by millions of years. But unless the laws of physics themselves differ in their region of space, something for which there is no evidence, they face the same relativistic barrier. And that barrier does not weaken with intelligence. It is written into the metric of spacetime. Thus, when we ask whether aliens can ever reach Earth, we must not ask whether they are clever enough. We must ask whether they can overcome infinite energy requirements, exponential scaling, cosmic expansion, and multi-millennial timelines imposed by a universal speed limit. The second keynote is not dramatic. It is mathematical, and mathematics, as Feynman would remind us, does not care what we prefer. It tells us that the faster you try to go, the harder the universe pushes back. Approach light speed, and the resistance becomes absolute. The closer you come to the boundary, the more violently energy demands explode. In that explosion of required energy lies a sobering truth. The cosmos is structured to prevent shortcuts. The speed limit, it is not merely a number. It is a guardian of causality, and it stands as the second immense barrier between Earth and any civilization that might look toward us from beneath another distant sun. As we continue deeper into the implications of the universal speed limit, the consequences become even more unforgiving. The barrier imposed by relativity is not simply about how fast a spacecraft can go. It reshapes energy, momentum, mass, time, and even causality itself. And when we follow those implications carefully, with the disciplined skepticism that Richard Feynman championed, we begin to see that the speed limit does more than slow civilizations down. It cages them within light cones. To understand this, imagine spacetime not as empty distance, but as a structured arena where every event has a future and a past bounded by light speed. If something occurs here on Earth right now, its influence spreads outward at the speed of light. That expanding sphere defines what can ever be affected by us. Anything outside that sphere remains causally disconnected, unreachable in principle until sufficient time passes. This is not philosophy, it is geometry. Every civilization, no matter how advanced, lives inside such a causally expanding bubble. Even if aliens developed propulsion systems reaching 999% of light speed, they would still remain confined within the structure of spacetime. They cannot step outside it. They cannot outrun it. Now let us press further into the energy problem, because it becomes even more brutal at extreme velocities. The relativistic kinetic energy equation shows that as velocity approaches light speed, total energy increases without bound. Consider a spacecraft with a mass of 1 million kilograms, modest by interstellar standards if shielding, habitat systems, and propulsion are included. To accelerate such a craft to 99% of light speed would require on the order of 10-19 joules or more. That is comparable to humanity's total energy consumption over many years, and that is only for acceleration in one direction. But the situation is worse. To arrive at a destination safely, you must decelerate. That doubles the energy requirement. And unless you have a braking mechanism external to your craft, such as a precisely aimed stellar laser array waiting at your destination, all deceleration energy must also be carried aboard as fuel or stored potential. Fuel adds mass. Added mass increases required energy. Increased energy demands more fuel. The feedback loop is punishing. This is known as the tyranny of the rocket equation. Even before relativity enters, exponential fuel requirements plague high-speed travel. Once relativistic effects begin to dominate, the burden compounds. Some propose antimatter propulsion. Matter-antimatter annihilation converts mass into energy with extraordinary efficiency. But antimatter production is immensely difficult. Even with advanced technology, producing and storing significant quantities safely presents enormous engineering challenges. Antimatter must be contained without touching normal matter. A containment failure would release catastrophic energy instantly. Even if an alien civilization mastered antimatter at scale, they still confront the relativistic wall. No propulsion system bypasses the Lorentz factor, and the faster you travel, the more dangerous the interstellar medium becomes. At everyday speeds, interstellar space is sparse, but at 99% of light speed, even a single hydrogen atom becomes a high-energy projectile. Collisions at relativistic speeds generate radiation bursts and particle showers. Microscopic dust grains strike with the force of explosive shells. Shielding must be extraordinarily thick or electro-magnetically sophisticated. That shielding adds mass. Mass increases energy demand. Energy demand increases fuel. The chain tightens. Even cosmic background radiation becomes blue-shifted into higher. Energy forms in the spacecraft's frame. What appears as microwave radiation at rest transforms into potentially damaging radiation at near light speed. The ship effectively plows through a particle accelerator environment of its own making. The speed limit thus introduces a secondary barrier. As velocity increases, the universe itself becomes more hostile. Feynman often delighted in how different physical effects interlock. Here, relativity does not operate alone. It couples with particle physics, thermodynamics, and electromagnetism to create cascading constraints. Now let us address a common speculative escape: warp drives. The idea of bending spacetime, compressing space ahead of a ship, and expanding it behind, originates from solutions to Einstein's equations. These solutions, such as the Alcubierre metric, suggest that spacetime geometry could allow effective faster and light travel without locally exceeding light speed. But mathematics alone does not guarantee physical realizability. These solutions require exotic matter with negative energy density. Negative energy is not simply rare. It is not known to exist in macroscopic, stable forms. Certain quantum effects, like the Casimir effect, produce tiny regions of negative energy density, but scaling such phenomena to spacecraft levels appears implausible. Moreover, estimates suggest the energy required to generate a warp bubble large enough for a vessel could rival the mass, energy of entire planets or stars. Even if theoretical refinements reduce this requirement, it remains speculative and experimentally unsupported. Feynman would caution against confusing mathematical permissibility with physical feasibility. The equations of general relativity allow many exotic geometries. Nature does not necessarily implement them. Then there are wormholes, hypothetical tunnels connecting distant regions of spacetime. Like warp metrics, traversable wormholes require exotic matter to remain open. Without stabilization, they collapse instantly. And even if naturally occurring wormholes exist, finding one, accessing it, and ensuring it leads to a desired destination introduces layers of uncertainty bordering on impossibility. Thus far, every experimental test confirms that causality and light speed constraints hold universally. Now let us consider another subtle implication of the speed limit: synchronization breakdown. Suppose an alien civilization launches a fleet at 95% of light speed toward Earth from 0 light years away. In their frame, due to time dilation, perhaps only a few hundred years pass during the voyage. But from Earth's frame, over 0 years elapse. During that time, Earth's civilization evolves, languages transform, political systems shift, technology leaps unpredictably. The aliens depart toward a target defined by 21st century conditions. They arrive to a civilization perhaps unrecognizable or extinct. The speed limit guarantees informational delay. You cannot know current conditions of a distant target beyond the time light takes to reach you. If a civilization 0 light years away detects Earth's radio emissions today, what they observe reflects Earth 0 years ago. If they launch immediately, they are aiming for a historical snapshot, not a living present. Travel and knowledge are always out of sync across cosmic distances. The speed limit thus ensures that interstellar journeys are acts of extreme uncertainty. Now widen the scale again. The Milky Way rotates. Our Sun orbits its center approximately every 225 million years. Other stars move at different velocities and trajectories. Over tens of thousands of years, relative stellar positions shift substantially. Navigation requires extraordinary predictive precision. Any deviation, any gravitational perturbation, any miscalculation in initial trajectory magnifies over light years. Minor errors compound into catastrophic misses. And because no signal travels faster than light, course corrections depend on delayed information. If a ship deviates slightly, confirmation of that deviation takes years to detect from home base. Autonomous correction systems must operate flawlessly for centuries. Again, the speed limit multiplies complexity. Let us now address cosmic expansion in greater depth. On intergalactic scales, galaxies recede from one another due to the expansion of space described by the Friedmann-Lemaitre equations. Beyond a certain distance, roughly 16 billion light years in comoving coordinates, regions recede from us faster than light due to metric expansion. This does not violate relativity because it is space itself expanding, not objects moving through space. But the result is profound. Signals sent today from beyond that horizon will never reach us. Likewise, we cannot send signals or spacecraft to reach them. The observable universe is not the entire universe. It is merely the region within our light cone since the Big Bang. Even if a advanced civilization existed in a galaxy receding beyond our event horizon, contact is fundamentally impossible. The speed limit, combined with cosmic expansion, partitions the universe into permanently isolated regions. Isolation is not an accident. It is a structural outcome of relativistic cosmology. Now step back philosophically. The speed of light limit protects causality. Without it, paradoxes proliferate. Information could travel backward in time. Events could influence their own causes. The logical consistency of physics would unravel. Thus, the same barrier that frustrates dreams of alien visitation also preserves the coherent structure of reality. Feynman respected that balance. He understood that constraints are not arbitrary punishments. They are often necessary for deeper consistency. In that sense, the universe trades interstellar convenience for causal order. And so we reach a sobering recognition. If aliens exist within a few dozen light years near light's speed, travel might, in principle, allow contact within manageable timescales. But if they are separated by hundreds or thousands of light years, the speed limit stretches travel into epochs. If they exist in distant galaxies, cosmic expansion seals the boundary. If they attempt relativistic travel, energy requirements explode. If they attempt speculative spacetime engineering, they confront exotic matter requirements and unverified physics. At every turn, the speed limit reasserts itself. It is not a technological challenge waiting for clever engineering. It is a geometric feature of spacetime. The second keynote thus deepens the first. The cosmic scale problem tells us space is vast. The speed limit tells us that vastness cannot be crossed quickly. Distance alone might be manageable with infinite speed. Speed alone might be irrelevant in a small universe. But together, enormous distances and finite maximum velocity, they generate travel times that dwarf civilizations. Even optimism must bow to arithmetic. Feynman would not say aliens are impossible. He would say that any claim of routine interstellar visitation must confront relativity honestly. And when confronted honestly, relativity speaks clearly. No matter how intelligent a civilization becomes, no matter how long it evolves, it cannot exceed the speed of light. It cannot reduce travel times below distance divided by that constant. It cannot escape causality's boundary. And in that simple, elegant, relentless limit lies the second immense wall separating Earth from distant stars. The universe does not forbid intelligence, but it does forbid shortcuts. Now we move into a barrier that is even more merciless than distance or speed limits alone: energy. Not abstract energy, not speculative energy, but calculable, measurable, brutally quantified energy. Because even if we imagine a civilization willing to endure thousands of years of travel, and even if we accept that nothing can exceed the speed of light, we must still confront the most unforgiving question of all: how much power does it actually take to cross interstellar space? This is where romantic visions collapse under arithmetic. Richard Feynman believed that when numbers are placed honestly into equations, illusions tend to disappear. He was not impressed by grand claims unless the mathematics agreed, and when we run the numbers for interstellar propulsion, the results are staggering. Consider a spacecraft with mass. It does not need to be enormous. Let us imagine a vessel weighing 1 million kilograms, the mass of a large naval ship on Earth. That mass would include structural components, radiation shielding, propulsion systems, life support, scientific instruments, and possibly a crew or biological cargo. To accelerate that mass to even 10% of the speed of light requires an almost inconceivable amount of energy. Using classical kinetic energy as a rough approximation, and noting that relativistic effects will increase the requirement further, the energy required would be on the order of 5 times 1020 joules. To put that into perspective, total annual energy consumption for human civilization is roughly 6 times 1020 joules. In other words, accelerating a single million kilogram spacecraft to just 10% of light speed would consume energy comparable to nearly a year of total human energy usage, and that accounts only for acceleration. You must also decelerate upon arrival, doubling the energy requirement, and this is only 10% of light speed. At higher velocities, relativistic effects amplify the demand dramatically. At 50% of light speed, the energy requirement increases by more than an order of magnitude. At 90%, it explodes further. At 99%, the numbers approach levels comparable to the total energy output of stars over significant intervals. Energy does not scale linearly with speed at relativistic velocities. It grows steeply, punishingly, and energy must come from somewhere. Chemical rockets, like those used to reach orbit, are laughably inadequate for such missions. Their energy density is far too low. Even nuclear fission, splitting atoms, provides only a modest improvement relative to what interstellar travel demands. Fusion, the process that powers stars, offers greater energy density. But controlled fusion remains technologically difficult even for humanity's most advanced laboratories. And even if mastered perfectly, the fuel requirements for accelerating massive spacecraft to relativistic speeds would still be immense. Antimatter represents the most energy-dense known fuel, converting nearly 100% of mass into energy upon annihilation with normal matter. But producing antimatter is extraordinarily inefficient with known physics. Current particle accelerators generate minute quantities at enormous energy cost. Storing antimatter safely presents another extreme challenge, as it must be prevented from contacting ordinary matter at all times. Even an advanced alien civilization would face fundamental thermodynamic limits in antimatter production and storage. The containment systems alone would need to be extraordinarily reliable. A single containment failure would release catastrophic energy equivalent to nuclear detonations. And beyond the fuel itself lies the tyranny of the rocket equation. The rocket equation dictates that to accelerate a spacecraft, you must expel reaction mass. The faster you want to go, the more propellant you must carry, but propellant adds mass. More mass requires more propellant to accelerate that mass. The relationship becomes exponential. This creates a vicious cycle. If you want to double your velocity, you do not merely double your fuel, you may need several times more, depending on exhaust velocity. As speeds approach relativistic regimes, the situation becomes even more severe. Unless propulsion systems exist that do not require carrying massive amounts of onboard fuel, such as laser-driven light sails powered by external energy sources, the energy and mass burdens become overwhelming. But even external propulsion systems introduce new problems. A civilization would need to construct colossal energy transmitters capable of delivering continuous power across light years. Maintaining beam focus over interstellar distances presents diffraction challenges. Any misalignment would mean total mission failure. Even assuming such engineering miracles are achieved, deceleration at the destination remains a problem unless a receiving infrastructure already exists there. The energy catastrophe is not just about generating enough power. It is about controlling it, storing it, converting it, and surviving it. When enormous amounts of energy are used in propulsion, waste heat becomes a deadly issue. No engine operates at 100% efficiency. Even small inefficiencies translate into immense heat production at relativistic energy scales. That heat must be radiated into space. Radiating heat in vacuum is slow and requires large surface areas. Large radiators increase spacecraft size and mass, further increasing energy requirements. The system spirals toward complexity. Then there is shielding. At high velocities, collisions with interstellar particles release tremendous energy. Shielding must absorb or deflect this energy. That shielding adds mass. Added mass increases propulsion energy requirements. The energy catastrophe compounds itself through every design requirement. Now consider mission scale. If a civilization wishes not merely to send a probe, but to send a colonization vessel, something capable of sustaining thousands or millions of individuals, the mass increases dramatically. The energy requirements scale accordingly. For a generation ship weighing billions of kilograms, the propulsion energy approaches stellar scale magnitudes. That is not metaphorical. It approaches the energy output of a star over measurable durations. Harnessing even a fraction of stellar output is not trivial. It implies megastructures, perhaps enclosing large portions of a star's radiation. Even if technically possible for a sufficiently advanced civilization, the construction of such infrastructure represents a project of unimaginable scale and duration. Would a civilization commit a significant fraction of its star's energy output for centuries or millennia simply to send vessels across interstellar space? Perhaps, but the energy commitment would rival planetary industrial output over enormous timescales. And that is only for one mission. If the galaxy contains millions of stars with habitable planets, why choose distant targets requiring extreme energy expenditure when closer ones exist? Energy economics alone suggests that interstellar expansion would proceed slowly, incrementally, hopping to nearby stars rather than leaping across thousands of light years. The energy catastrophe enforces gradualism. Rapid galaxy spanning invasions as depicted in fiction would require absurd energy mobilization. Coordinating fleets traveling at relativistic speeds multiplies energy requirements across each vessel. The combined demand becomes astronomical. Even an advanced civilization likely operates under energy optimization principles. Physics encourages efficiency. The larger the velocity, the worse the energy return per unit of speed gained. This brings us back to a principle Feynman often emphasized. Nature is efficient but unforgiving. You can do many things within physical law, but you cannot cheat thermodynamics. The first law of thermodynamics demands energy conservation. The second law ensures that energy transformations produce entropy. There is no free propulsion. There is no free deceleration. Every joule must be generated, directed, and eventually dissipated. Now extend this reasoning to distances beyond our local stellar neighborhood. Suppose an alien civilization 1, 0, 0 light, years away considers traveling to Earth at 20% of light speed. The energy requirement for a single large vessel would already be immense. Multiply that by deceleration, shielding, redundancy, safety margins, and possible fleet size. The energy cost begins to resemble a civilization-level economic decision, not an exploratory whim. And remember, if they are 1000 light years away, what they know about Earth is 1000 years old. They are investing astronomical energy into reaching a planet whose present condition is unknown. Energy magnifies uncertainty. The farther you go, the more energy you expend. The more energy you expend, the greater the risk if the destination proves unsuitable, hostile, or transformed. Energy and risk intertwine. There is also a subtle sociological dimension. A civilization capable of harnessing stellar energy might find greater returns in local optimization, building habitats, manipulating planetary systems, exploring nearby stars slowly over millions of years, rather than expending colossal energy to leap across vast galactic gaps. Energy economics may discourage dramatic interstellar excursions. The universe does not forbid interstellar travel outright, but it prices it extraordinarily high. And when the price is measured in stellar output, multi-generational engineering, and near-total energy mobilization, feasibility narrows sharply. The energy catastrophe thus joins distance and speed limits as a reinforcing barrier. Distance sets the journey length. The speed limit caps how quickly it can be crossed. Energy determines whether even that capped speed is achievable. Each constraint strengthens the others. Feynman would likely conclude not with absolute prohibition, but with sober assessment. The laws of physics do not say interstellar travel is impossible, but they demand such extreme energy commitments that routine, frequent, or casual travel across large portions of the galaxy becomes extraordinarily improbable. Energy is the currency of motion, and the cosmos charges dearly. When we run the numbers honestly, when we multiply mass by velocity squared, account for relativistic growth, double for deceleration, add shielding, include inefficiencies, the dream of easy alien visitation evaporates. What remains is not fantasy. What remains is arithmetic. Even if we imagine that a civilization has solved the problems of distance, accepted the universal speed limit, and somehow gathered the staggering energy required for relativistic travel, another barrier emerges, one that is subtle, counterintuitive, and deeply rooted in the structure of spacetime itself. This barrier is time dilation and the one-way journey problem. To understand it clearly, we must once again think with the intellectual discipline of Richard Feynman. Feynman insisted that when physics produces strange consequences, we do not reject them because they feel uncomfortable. We follow the equations wherever they lead, and the equations of relativity lead to a profound and unsettling conclusion. The faster you travel, the more time itself changes. According to the theory of relativity developed by Albert Einstein, time is not absolute. It is not the same everywhere for everyone. Instead, time depends on motion. When an object moves at speeds approaching the speed of light, time for that object slows down relative to observers who remain at rest. This is not science fiction. It has been experimentally confirmed. Atomic clocks flown on airplanes tick slightly slower than identical clocks on Earth. Particles in accelerators live longer when moving at relativistic speeds. Time dilation is measurable and real. Now imagine an alien spacecraft traveling at 90% of the speed of light toward Earth from a star 1000 light years away. From Earth's perspective, the journey would take a little over 100 years. That is simply distance divided by velocity. But from the perspective of those aboard the spacecraft, time would pass more slowly. Perhaps only a few hundred years would be experienced on board, depending on the exact speed. At first glance, this seems helpful. It appears to reduce the subjective burden of travel. The crew might age only a few centuries, while more than a millennium passes outside. But this is where the deeper consequence appears. Time dilation does not shorten the journey in the external frame. It merely desynchronizes the travelers from the universe they are traveling through. When the ship arrives at Earth, over 1,000 years will have passed here. Civilizations will have changed. Species may have evolved or vanished. Coastlines may have shifted. Political systems will be unrecognizable. The aliens depart toward a world defined by information that is already centuries old when they receive it. By the time they arrive, that world has aged dramatically beyond their expectations. Time dilation therefore creates a one-way relationship between traveler and destination. The faster you go, the more detached you become from the timeline of the place you are approaching. Now consider the return journey. If the aliens decide to return home after arrival, they must repeat the entire process. From their perspective, perhaps a few hundred more years pass, but in their home star system, thousands of years may have elapsed. The civilization that launched them may no longer exist. Governments may have collapsed. Species may have transformed. Languages may have evolved beyond recognition. Entire planets may have undergone climate shifts. Relativistic travel fractures synchronization permanently. The deeper you push into relativistic speeds, the more severe the dislocation becomes. Suppose instead the ship travels at 99% of light speed. Time dilation becomes extreme. The travelers may experience only decades, while thousands of years pass outside. But this intensifies the one-way problem. They arrive in a future that is no longer meaningfully connected to the past they left. Communication suffers similarly. If a civilization 2,000 light years away detects Earth signals today, what they observe reflects Earth 2,000 years in the past. If they respond immediately, their reply arrives here 2,000 years from now. A full exchange requires 4 zeros, 0 years. Relativity ensures that conversation across interstellar distances is staggered across millennia. Now consider the psychological dimension. A mission launched at relativistic speeds is not merely a long journey, it is a temporal exile. The travelers leave behind not only space, but time. They cannot remain synchronized with their origin civilization. They cannot participate in its development. They cannot even be certain it still exists upon arrival home. For sufficiently long journeys, the concept of return loses meaning. This is the essence of the one-way journey problem. Any civilization attempting relativistic exploration must accept that its explorers effectively sever themselves from their historical context. They become temporal migrants into a distant future. Now imagine scaling this to galactic distances. The Milky Way spans roughly 100,000 light years. Even at 99% of light speed, crossing the galaxy would require over 100 years in the external frame. The travelers might experience much less due to time dilation, perhaps only thousands of years, but the galaxy itself would age by 100 millennia. Stars move in their orbits, stellar clusters disperse, supernovae occur, new stars are born, civilizations rise and fall countless times. A civilization attempting to traverse large fractions of the galaxy at relativistic speeds is effectively leaping forward in time relative to the broader cosmic environment. Exploration becomes time travel into the future. This creates another profound issue: strategic irrelevance. If a civilization intends to expand, colonize, or interact, it must coordinate across time. But relativity ensures that synchronization across thousands of light years becomes impossible on human or even biological timescales. Colonies established 5,000 light years apart cannot coordinate in real time. Decisions made in one region reach another thousands of years later. Political unity across such distances becomes implausible. Relativistic travel fragments civilizations into causally disconnected pockets. Even if aliens had the capability to reach Earth, they would face a severe dilemma. Are they explorers, prepared never to return? Are they colonists, willing to abandon their origin permanently? Are they probes, sent without expectation of reunion? Every mission becomes existential. Now consider the implications for Earth specifically. If an alien civilization 10,000 light years away launches a ship toward us at 95% light speed, from our perspective, the ship will not arrive for over 500 years. Humanity itself may not survive that long. Our species has existed in its current form for roughly 300 years, but technological civilization is only a few thousand years old. Projecting even 10,000 years into the future involves enormous uncertainty. Climate change, asteroid impacts, self-destruction, biological evolution, all are possible. Thus, a civilization attempting to reach Earth must invest vast energy into a journey toward an unknowable future. Time dilation does not protect them from this uncertainty. It only isolates them from it, and the faster they travel, the more extreme the dislocation. There is a subtle irony here. Relativity makes extreme travel theoretically survivable in subjective time, but it simultaneously guarantees that the universe outside evolves far beyond the departure conditions. The traveler ages slowly, the cosmos does not. This asymmetry undermines any notion of routine interstellar interaction. Civilizations become like sparks flickering in different eras, separated not only by space, but by asynchronous timelines. Feynman often emphasized that physics is not obliged to align with human desires. The relativity of time is a perfect example. It is elegant, mathematically consistent, experimentally verified, and devastating to dreams of galactic cohesion. Even if an alien civilization could overcome distance, speed, and energy, it cannot overcome desynchronization. Time dilation ensures that relativistic voyages are effectively one way into the future. The return home is not a reunion. It is arrival in a distant epoch. And when civilizations operate on timescales of centuries or millennia, such dislocation becomes culturally destabilizing. Would a civilization repeatedly send missions that permanently severed generational continuity? Perhaps. But not casually, not frequently, not across vast galactic distances. Thus, time itself becomes a barrier. Not because it stops motion, but because it fractures connection. Interstellar travel at relativistic speeds does not merely move through space. It tears travelers out of shared time, and in that tearing lies another immense, often overlooked obstacle to the idea that aliens can easily reach Earth. The universe does not only separate us by distance, it separates us by chronology, and that separation grows more severe the faster you try to cross it. Even if we imagine that a civilization has solved the problems of distance, accepted the universal speed limit, gathered unimaginable energy, and embrace the one-way temporal consequences of relativistic travel, there remains another barrier, one that is less glamorous but brutally practical. Space itself is hostile, not empty in a gentle sense, but empty in a lethal one. From a distance, space appears calm and silent. But silence does not mean safety. The vacuum between stars is saturated with radiation, high-energy particles, magnetic fields, and microscopic debris moving at enormous velocities. The deeper we examine the physical environment beyond planetary atmospheres, the clearer it becomes that surviving interstellar travel is not simply about propulsion. It is about enduring a cosmic firing range for decades, centuries, or millennia. Richard Feynman would insist that we examine this environment quantitatively, not romantically. Space is not a smooth highway. It is an arena governed by particle physics and thermodynamics. Let us begin with radiation. On Earth, we are shielded by two extraordinary protections, our atmosphere and our magnetic field. The atmosphere absorbs harmful ultraviolet radiation, X-rays, and gamma rays. The magnetic field deflects charged particles streaming from the sun and from deep space. Remove those shields, and life becomes vulnerable immediately. Interstellar space contains cosmic rays, high-energy protons, and atomic nuclei accelerated by supernova explosions and other energetic astrophysical events. These particles travel at nearly the speed of light. When they collide with biological tissue, they damage DNA at the molecular level. Short-term exposure increases cancer risk. Long-term exposure across decades becomes devastating. Even inside our own solar system, astronauts aboard the International Space Station receive significantly higher radiation doses than people on Earth. Missions to Mars must carefully account for solar flares and cosmic radiation. That is within a relatively protected region of space. Interstellar travel would expose travelers to continuous cosmic radiation for years or centuries. Shielding is possible, but shielding requires mass. Thick layers of water, metal, or specialized materials can absorb radiation, but mass increases propulsion energy requirements dramatically. Every kilogram added for protection must be accelerated and decelerated, and shielding has limits. High-energy cosmic rays can penetrate substantial material thickness. When they strike shielding, they can produce secondary particle showers, creating additional radiation inside the spacecraft. Designing effective shielding against relativistic particles is not trivial. Now consider velocity. If a spacecraft travels at a significant fraction of the speed of light, the radiation environment becomes even more severe. Interstellar hydrogen atoms, normally sparse and harmless, become high-energy projectiles in the ship's reference frame. At 90% of light speed, even a single hydrogen atom striking the front of a spacecraft carries kinetic energy comparable to a particle accelerator beam. Multiply that by countless collisions over years of travel, and the cumulative effect becomes substantial. Microscopic dust grains present an even greater threat. Interstellar space contains tiny particles, fragments of rock, ice, and carbon compounds, often no larger than grains of sand or smaller. At ordinary speeds, they pose minimal danger, but at relativistic velocities, their impact energy scales with velocity squared and with relativistic correction factors beyond that. A grain of dust striking a ship at 50% of light speed would release explosive energy. At 90%, the impact could resemble a small detonation. Over the course of a decades-long journey, even sparse dust becomes statistically significant. To protect against this, a spacecraft would require heavy forward shielding or electromagnetic deflection systems capable of redirecting charged particles. But neutral particles cannot be deflected by magnetic fields. They must be absorbed physically. Again, mass increases. Energy demands increase. Complexity increases. And then there is the vacuum itself. Space is not just empty. It is empty of pressure. Life evolved under atmospheric pressure. Remove that pressure, and fluids boil at low temperatures. Biological systems require controlled internal environments, temperature, humidity, gas composition. Maintaining such an environment for decades or centuries without failure is an engineering challenge of extreme reliability. Even small system failures could cascade. A minor leak becomes catastrophic in vacuum. Mechanical systems degrade. Materials fatigue. Electronics suffer radiation damage. Over long timescales, entropy accumulates relentlessly. Machines fail. On Earth, failures can be repaired with external supply chains. In interstellar space, there is no resupply. A vessel must carry everything it will ever need. Redundancy multiplies mass. Self-repair systems increase complexity. And complexity increases failure probability. Consider biological survival across generations. If a journey lasts centuries, multiple generations would live and die aboard the spacecraft. Closed ecological systems would be required, fully self-sustaining biospheres recycling air, water, and nutrients indefinitely. Human attempts at closed ecosystems, such as experimental biosphere projects, have demonstrated how difficult perfect recycling is. Even minor imbalances can destabilize the entire system. Now extend that to a century-long mission without external input. The stability of such systems must approach perfection. Then there is psychological survival. Isolation over long durations introduces sociological instability. Confined populations may experience conflict, depression, or cultural drift. Governance structures must remain stable across generations. Space does not merely challenge engineering. It challenges biology and sociology, and the external environment never relaxes. Solar systems contain flares, magnetic storms, and radiation bursts. Interstellar space contains unpredictable cosmic events. A nearby supernova, even thousands of light years away, can increase radiation levels significantly. A spacecraft traveling for centuries cannot predict every astrophysical hazard it might encounter. Now imagine that such a vessel finally approaches Earth. After decades or centuries of exposure to radiation, micrometeoroid impacts, mechanical wear, and ecological strain, the spacecraft must decelerate, maneuver precisely, and enter a planetary system without catastrophic failure. One critical system failure during deceleration could destroy the mission entirely. The harshness of space transforms interstellar travel from a question of speed into a question of endurance against relentless environmental hostility. Let us examine temperature. Space is often described as cold, approximately 2.7 Kelvin due to the cosmic microwave background. But temperature in vacuum behaves differently. Objects exposed to direct starlight can become extremely hot, while shaded areas become extremely cold. Thermal regulation becomes complex, especially for long-duration missions crossing varying radiation fields. Materials expand and contract under temperature fluctuations. Over long timescales, such cycling degrades structural integrity. Even small cracks can propagate catastrophically in vacuum. Radiation also damages electronics. High-energy particles cause bit flips in computer memory, degrade semiconductor materials, and accumulate damage in circuits. Modern spacecraft use radiation, hardened components, but even these have limits. A century-long mission at relativistic speeds would expose electronics to cumulative radiation doses far beyond most current design lifetimes. Robust error correction systems would be essential. Self-repairing nanotechnology might be imagined. But such technologies must themselves be immune to radiation damage. Again, complexity breeds vulnerability. And beyond physical threats lies navigational precision. At high speeds, tiny errors magnify enormously. A slight misalignment early in the journey becomes a massive deviation across light years. Autonomous correction systems must operate flawlessly under radiation exposure and hardware degradation. The environment of space does not forgive mistakes. Feynman often pointed out that nature is subtle but not malicious. It does not set traps intentionally, but it does enforce consequences precisely. The vacuum does not care about ambition. Radiation does not care about exploration. Dust grains do not negotiate. The laws of particle interaction remain constant whether you are crossing a laboratory chamber or crossing 1,000 light years. And so, when we combine all these factors, radiation exposure, micrometeoroid impacts, thermal extremes, mechanical fatigue, closed system fragility, electronic degradation, sociological stress, we see that interstellar travel is not merely a matter of reaching high speed. It is a matter of surviving a continuous assault for durations far exceeding most engineered systems in human history. On Earth, infrastructure is replaced every few decades, bridges are rebuilt, power plants are upgraded. Spacecraft are retired after years, or, at most, a few decades. An interstellar vessel must function reliably for centuries without external maintenance. The probability of uninterrupted success declines with time. Even if the chance of catastrophic failure in any given year is small, over hundreds of years it accumulates. This is the tyranny of long durations in hostile environments. And remember, all of this assumes a single journey. If alien civilizations were routinely visiting Earth from distant stars, they would have solved not only propulsion and energy, but also the extreme survivability challenges posed by radiation. Dust, vacuum, entropy, and time, each barrier compounds the others. The harsh reality of space is not dramatic in the way science fiction portrays explosions and laser battles. It is quiet, it is persistent, it is statistical, and over long enough durations, statistics are merciless. Thus, even after distance, speed, energy, and time dilation are considered, the environment of space itself stands as a formidable wall. The cosmos is not designed for comfortable travel between stars. It is vast, cold, irradiated, and filled with invisible hazards moving at extraordinary velocities. To survive crossing, it is not impossible in principle, but it demands such extreme durability and precision that the probability of routine, repeated alien visitation shrinks further. Space does not simply separate civilizations. It tests them relentlessly across every kilometer of the journey. There is a haunting silence in the cosmos. It is not just poetic silence. It is measurable. It is scientific. It is the silence of unanswered signals, of empty skies, of telescopes that have searched for decades and found nothing conclusive. And this silence leads us to one of the most unsettling scientific questions ever formulated. If intelligent life is common in the universe, where is everybody? This question was famously raised by Enrico Fermi during a casual lunch conversation in 1950. Fermi was not prone to wild speculation. He was practical, numerical, and grounded in physical reasoning. When discussion turned to flying saucers and interstellar travel, he performed a quick mental calculation and asked a deceptively simple question: where is everybody? That question became known as the Fermi paradox. The paradox emerges from a tension between two ideas. On one side, the universe is vast and ancient. On the other side, we see no convincing evidence of alien visitors, probes, or civilizations. When we combine these two facts with basic physics and probability, the silence becomes puzzling. Consider the scale of our galaxy, the Milky Way. It contains roughly 100 to 400 billion stars. Many of those stars have planets. Since the discovery of exoplanets in the 1990s, we now know that planets are not rare accidents. They are common. Observations from missions like Kepler have shown that potentially habitable planets, rocky worlds in the right temperature zone, may be widespread. Our galaxy is also old. It is over 13 billion years old. Earth formed about 4.5 billion years ago. That means there were billions of years for life to emerge elsewhere before Earth even existed. If intelligent civilizations arose even a small fraction of the time, some of them could be millions or billions of years more advanced than we are. Now combine this with the idea of expansion. Even at modest sublight speeds, say 1% of the speed of light, a civilization could theoretically spread across the galaxy in tens of millions of years. That sounds long to us, but compared to the age of the galaxy, it is brief. If just one civilization had developed interstellar travel millions of years ago, it could have colonized, explored, or at least sent self-replicating probes throughout the galaxy by now. And yet, we see nothing unmistakable. No alien megastructures blocking starlight. No probes in our solar system sending clear greetings. No signals that cannot be explained by natural processes. Radio telescopes scanning the sky have detected intriguing anomalies, but none have been confirmed as artificial extraterrestrial communication. This is the heart of the paradox. If interstellar travel were physically achievable on a large scale, and if intelligent life were not extraordinarily rare, then the galaxy should already show signs of it. The silence suggests something is wrong with at least one of our assumptions. One possibility is that intelligent life is extremely rare. Perhaps the emergence of complex life requires such an improbable chain of events that it has happened only once, here. Maybe microbial life is common, but advanced technological civilizations are almost non-existent. Another possibility is that civilizations do arise, but they do not last long. Technological intelligence may carry within it the seeds of self-destruction. Nuclear war, ecological collapse, artificial intelligence misalignment, or other unforeseen dangers might prevent civilizations from surviving long enough to achieve widespread interstellar expansion. But there is a third possibility, one that connects directly to the physical arguments we have been discussing. Perhaps the laws of physics themselves act as a filter. Perhaps interstellar travel is not merely difficult. Perhaps it is so prohibitively expensive, slow, and dangerous that even advanced civilizations rarely attempt it. When we look honestly at the energy requirements of accelerating spacecraft to relativistic speeds, the shielding required to protect against cosmic radiation, the hazards of micrometeoroid impacts at near light velocity, and the immense timescales involved, interstellar travel begins to look less like an engineering challenge and more like a fundamental barrier. If even one of these barriers is insurmountable in practice, if propulsion beyond certain speeds remains impossible without absurd energy costs, then the galaxy becomes effectively disconnected. Civilizations may exist, but they remain isolated in their own star systems, separated by gulfs too vast to bridge physically. In that case, the silence is not mysterious. It is inevitable. There is also the possibility that civilizations communicate differently than we expect. We search for radio signals because radio was our first long-distance communication technology. But advanced civilizations may use methods we have not imagined or cannot detect. Our instruments may be too primitive. Our search window may be too narrow. Still, the fact remains that no credible evidence of alien visitation has ever been verified. Extraordinary claims of crashed saucers and secret recoveries have never survived rigorous scrutiny. And this is where the spirit of Richard Feynman becomes essential. Feynman insisted that we must not fool ourselves, and we are the easiest people to fool. Wishful thinking is not evidence. Stories are not data. Anecdotes are not physics. If aliens were regularly visiting Earth, the evidence would not be ambiguous. It would not hide in blurry photographs or inconsistent testimonies. It would be overwhelming, repeatable, and measurable. The paradox, then, strengthens the physical argument against alien visitation. If interstellar travel were easy for advanced civilizations, we would likely see clear evidence by now. The fact that we do not suggests either that such civilizations are extraordinarily rare, or that the physics of interstellar travel is a far greater obstacle than popular imagination assumes. Some have proposed that advanced civilizations might choose not to interfere, following a kind of cosmic prime directive. Others suggest they may observe silently. But even silent observers would likely leave detectable technological signatures, waste heat, altered planetary atmospheres, engineered structures. So far, nothing has been confirmed. The Fermi paradox does not prove that aliens do not exist. It does not prove that life is rare. It simply sharpens the question. It forces us to confront the gap between what seems statistically plausible and what is physically observable. And when we combine this paradox with the known limits imposed by relativity, energy constraints, radiation hazards, and timescales, the conclusion becomes sobering. The universe may be filled with life, yet still be effectively unreachable. Intelligence may arise again and again, only to remain confined to its local star, forever separated from others by distances that no technology can practically conquer. In that sense, the silence of the cosmos may not be a sign of emptiness. It may be a sign of isolation. The night sky appears full of stars, but each star may be an island universe, surrounded by an ocean so vast and so unforgiving that crossing it is not just unlikely, it may be physically unrealistic on any meaningful timescale. And so we return to Fermi's simple question, where is everybody? Perhaps they are out there, asking the same question about us. Perhaps they too look into their night sky, calculate the energy requirements, confront the speed of light, and conclude that the gulf is too wide. The paradox does not end with an answer. It ends with humility. It reminds us that the universe operates according to laws that do not bend for curiosity or ambition. If aliens could easily reach Earth, the evidence would likely already be here. The fact that it is not may be telling us something profound, not about the absence of life, but about the limits imposed by physics itself. If you found this deep exploration of science and the mysteries of the universe fascinating, don't forget to support the journey. Your curiosity keeps real scientific discussions alive. Please like this video, share it with friends who love physics and big cosmic questions, and drop your thoughts in the comments below. What do you think? Are we alone, or just isolated by the laws of physics? Subscribe to our channel Science with Research and turn on notifications so you never miss our next in-depth scientific breakdown. See you in the next video.